Yeah, this talk is a bit meta, and certainly the focus in the title is on the algebra, but nothing too sophisticated. Some basic ring theory, finite groups, permutation groups, and of course cohomology. So I thought it was a good opportunity at this meeting, given the length of time from the previous one, to revisit some of the major problems in what we call algebraic design theory that haven't been fully resolved. So to advertise these problems and advocate for their solution. Now, I'm going to be talking about work that is joined with several people. First and foremost, Warwick Delaney, also Kathy Hardham, and a few other people who were here at this meeting, Andres Bordrig and Ronan. But we've also got to be aware of complementary approaches, and here are a few of those. Firstly, due to Nobuo Ito, for Hadamard matrices in particular, those sorts of pairwise combinatorial designs, his idea of Hadamard groups, Rob's theory of sign groups as part of an alternative philosophy to algebraic design theory, and of course there's the work by Giora and Asif Goldberger on cohomology development. So given the constraints, I've had to pitch the talk at a level where a lot is going to be left out. So for missing proofs and all of the gory details and a whole lot more, my disclaimer is to consult our book with Warwick, where you can find full justifications and explanations for things in this talk, and as I say, much more. Right, so what is the fundamental object of interest in this meta theory? So for us, a design is a pairwise combinatorial design, PCD, and we distill the essence of the design into an orthogonality set. What distinguishes these designs is that if we take every pair of rows of our design, which is a square matrix over some specified alphabet, that every pair of rows lies in some specified orthogonality set. Now, there are more things involved in this definition that I've written down for the moment, but it's so general that, and this is the intention, that we capture all of the familiar instances of designs that are studied, individually. And here is a sample of those. But you can push this abstract notion a lot further. Okay, so pairwise combinatorial design. Every pair of rows is contained in this specified orthogonality set. So the idea is to do as much as you can with the orthogonality set to get implications about the designs. And just to give a couple of examples for PCDs that have been of high interest this week, Hadamard and Wayne matrices here is a sort of obvious orthogonality set definition for each of those. So right from the beginning, we're starting to see themes emerging. Firstly, you'll notice that each of these orthogonality sets is given by a Grahamian condition. So we're doing matrix algebra over some implicit ring. What is that ring? Well, for these two cases, for Hadamard ring matrices, take basically any ring of characteristic 0. The other thing that's apparent in the example for the two examples here is that the orthogonality set is invariant under permutation equivalence operations, permuting columns, swapping rows. You stay within inside the orthogonality set. So that's actually part of the definition of any orthogonality set is invariant under these very basic equivalence operations, permutation equivalence operations. Right. So that's very abstract. Let's look at some concrete examples. So I'll leave you to check that this is a generalized Hadamard matrix. In this case, over the cyclic group of order 4 generated by C. Perhaps the construction is, the block matrix nature of the design here. The construction method might be sort of understandable as a Kronecker type construction. So what makes this a generalized Hadamard matrix is that its Gramian satisfies the following condition. The star here means take the transpose and apply a ring involution to matrix entries. Inversion on the group G extended to, in this case, our ambient ring is the group ring over the integers, say, or the rationals, if you want. Okay, generalized Hadamard matrix over a group. I just want to say, point out another fact about these. For a long time, all of the known examples were over abelian coefficient groups. Warwick discovered a construction for any finite P group as the coefficient group. But certainly all known examples have the coefficient group a finite P group. And there's a reason for this. There is a connection to existence of finite projective planes, existence of generalized Hadamard matrices versus finite projective planes. Okay, another class of PCD that has been of interest this week are the Butson Hadamard matrices. And here, just by way of concrete example, the two inequivalent Butson Hadamard matrices over the 6th roots of unity, 7 by 7 over the 6th roots of unity. Okay, now just the standard caveat as regards BH versus GH. If we have a GH over a cyclic group, then we can get a BH over the roots of unity of that order. But in the opposite direction, not in general. Apart from the case when we're looking at a cyclic group of primary, then Butson Hadamard matrix and generalized Hadamard matrix are the same thing. Okay. So I want to continue the discussion, focusing on a few themes that have arisen in the examples so far. And the first of these is dealing with standard equivalence operations on designs, PCDs. So sticking with Butson Hadamard matrices, for example, if we commute rows, commute columns, multiply any row by an element of the alphabet, any column by an element of the alphabet, starting from the BH, we end up with the BH with the same parameters. And how do we do this in practice? By simple matrix algebra. Okay, pre-multiplied by a monomial P over the kth roots of unity, post-multiplied by a monomial Q star. The star on the right, in the post-multiplication, is there so that we can define an action eventually, and thereby the orchestral group of a pairwise combinatorial design. Now, we want to be able to do this always. Can we do this always? Starting from the abstract notion of orthogonality set, do we always? Can we always model the familiar, the standard equivalence operations in this way using matrix algebra? So we need to show that there always exists a ring an ambient ring that makes this possible. And that can be done, that's been proved laboriously, so it's an abstract construction. In practice, we don't work with this ring. It's a monoid ring, rather certain homomorphic images of it. But this at least is the first success. There always exists an ambient ring, associative ring with one, and with a ring involution star, such that lambda equivalence operations can be affected by matrix multiplication in exactly this way, as for the special case of Bunsen-Hadamard matrices. Okay, so this is one of the first, obsessions of the theory, the proof of existence of ambient rings to deal with these major themes of design theory. The first of which, obviously, or naturally, is equivalence operations. So we can do that. We can show that there always exists a suitable ambient ring. What else? Well, it's got a bit else that we want to do, and so this next point is suggested by observation that the individual kinds of PCDs are equivalently defined by a Gramian condition. In other words, a candidate matrix D is a PCD for any fixed orthogonality set lambda, if and only if its Gramian lies in the set of Gramians of all PCD lambdas. It's not difficult to see that this will be guaranteed as long as the orthogonality set has this Gramian property. The candidate element of the a candidate for being in lambda is in lambda if and only if its Gramian is in the set of Gramians of all elements of lambda. And we also proved that such an ambient ring always exists for any orthogonality set. But what we don't have a complete answer to is this question: is there a ring to take care of both these requirements at the same time? It's yes. So I guess we're reminded here, for people who know Tolkien, of how does it go again? One ring to rule them all, or one ring to bind them, etc. So that, I guess, is the first outstanding problem that I wanted to draw your attention to. It's a purely ring theoretic problem. But okay, moving on. So we've dealt with the lambda equivalence, the Gramian property, and eventually we want to specialize down to a ring that models co-cyclic development. Okay, now here the discussion begins with the idea of the automorphism group of a pairwise combinatorial design. Now, the orthogonality set is kind of fading away at this stage, but I'll talk about PCDs in these definitions because that's the eventual application. But these ideas are purely algebraic, matrix algebraic. So effectively, we've got an action of all monomial matrix pairs on the set of all matrices with entries in the alphabet for the orthogonality set. And the automorphism group of a particular matrix D, or PCD, for lambda, is the stabilizer of that D under this action. So the automorphism group of D, just to repeat, is the set of all pairs of monomials PQ such that PDQ star is equal to D. The orbit of D is its equivalence class, lambda equivalence class. So Warwick observed early on prevalence of many kinds of PCDs whose automorphism groups give rise to regular actions. So this is the hot word here, regular actions on arrays, on matrices. And a very interesting, very difficult question is whether there always exists PCDs with this property, with these associated regular actions. Special case of that general question is the co-cyclic Hadamard conjecture. This was the hope in the beginning that this algebraic idea would give us a way to make great progress on the existence question in general for PCDs, because this property of co-cyclic development seems to be so common. Anyway, the base case of co-cyclic development is group development, an algebraic idea. So a matrix is group developed if it is an image of a multiplication table for a group. Okay, we can index the rows and columns of D by the elements of the group G. So, I mean, here, this matrix is group developed over G. Being group developed over one group, it can be group developed over other non-isomorphic groups. So there's a fixed map 5 such that the entry in row X, column Y is 5x times Y. So as I say, an image of the multiplication table for a group. And this turns out to be, can be proved quite explicitly, that a matrix is group developed over G if and only if G acts regularly on it. Now that is shorthand for something more complicated. So what I'm saying here is that we've got pairs of permutation matrices fixing D such that the induced action on the rows and on the columns, those actions are both regular. So explicitly what's going on here is that G is acting via the right regular permutation representation on itself on the rows, and on the columns is acting via the left regular permutation representation of G on itself. And as you can see, the combined effect of those row and column actions is null. So so to say that the overall action by pairs of permutation matrices, a group isomorphic to G, to say that that's regular, this is what I mean, the induced row and column actions are both regular. Right, so this is the hot word, as I say, regular actions on arrays, starting with group development and then generalizing to cocyclic development. And the definition of regular group action, if it's needed. Right. So, I mean, there's no orthogonality sets here. This is an algebraic, entirely algebraic concept, group development. But you know, it does give a toehold. It gives us some you know, algebraic structure and then algebraic tools, in particular computational algebra, to study existence and classification problems for PCDs. The drawback is that when you do bring in the combinatorial constraint and start talking about group development of PCDs, not just you know, arbitrary matrices, then we encounter significant constraints. Here is one example of that. Group developed Wayne matrix must have square weight. So, you know, the propaganda for cocyclic development is it's more general than group development, doesn't impose these restrictions, and just to repeat, seems to be so widespread amongst various kinds of PCDs. So, unfortunately, or whatever, I'm going to have to just recite some of the standard cohomology theory. Some of this has appeared in talks earlier this week. What I want to emphasize is that our cohomology is with trivial coefficients. It's the nicest, simplest case. So take groups G and U, an abelian group U. So here is what a cocycle from G cross G into U is, a map satisfying this cocycle defining equation star. A set of all cocycles forms a group under pointwise multiplication Z2. We assume that this is just a convenience, we assume that cocycles are normalized, and if we write out our cocycle in full, its matrix, cocyclic matrix, then what this means is that the first row and the first column, starting your indexing with the 1 of the group, the first row and the first column are all 1. All right, so we've always got, we can always bring out cocycles to begin with these co-boundaries, and they form a subgroup of Z2. B2, and the quotient of those two abelian groups is the second cohomology group, formally of G with trivial coefficients in U. Okay, just to keep things concrete, let's focus on ±1 matrices only. for the moment. This generalizes, carries over to any U, but yeah. All right, so in this case, when U is ordered 2 generated by -1, we say that a cocycle is orthogonal if its matrix is a Hadamard matrix. Now, is something that means we can't ever ignore covariance. Cohomological equivalence does not respect orthogonality. In other words, within a cocycle class, you can have a mix of orthogonal and non-orthogonal cocycles. So if you're looking for these, in this case, where you're trying to construct Hadamard matrices, it's not enough to test one element from each cohomology class. Would that life was so simple? Yeah, that's it. So our search space, in naive terms, is exponential size. All right, now where do these cocycles come from? What I want to emphasize is that they appear very naturally, again because of an associated regular group action. In this case, on an expanded design. Now, just to repeat, we've got an expanded design in general for any coefficient group U, but this is what it looks like for U generated by -1. And I think you can see a permutation automorphism of EH by this element here, this involution here. Swaps row blocks and swaps column blocks. That takes you back where you started. So this is the theorem. The cocycle is forced into H, ±1 matrix in the expanded design, if and only if there is a regular group action on this expanded design, EH. As long as the regular group up top contains this special central involution. So it's regular group action. Now, if H happens to be a Hadamard matrix, so now we're bringing in orthogonality, then the group acting up top, this is what Ito calls the Hadamard group, and associativity of multiplication in this Hadamard group is exactly the cocycle defining equation. So that's where that comes from. Now, let's say a bit more about the orthogonality colliding with this algebraic notion of cocyclic development. So this little result is significant because it's one of the few results in the theory where the two things are meeting: the algebraic idea of cocyclic development and the combinatorics, PCD. So the result is that the cocycle sticking to ±1 coefficients is orthogonal if and only if in its matrix every non-initial row has zero sum. And the proof of this is quite nice. It just uses astute manipulations with the cocycle defining equation. So another way of saying this is that the cocycle is orthogonal if and only if its matrix has optimal row excess, has zero row excess. And this, I wanted to point out that this observation is the launching point for another avenue, notion of orthogonality, quasi-orthogonality for G of even order, not divisible by 4. So in this case, we say that the co-cycle is quasi-orthogonal if, again, in analogy, the row excess of its matrix is optimal. And the row excess in this case is 2 less than the group order. So this idea of quasi-orthogonal co-cycle is due to Andres and colleagues at Sevilla. And one of the reasons that quasi-orthogonal co-cycles are interesting is a connection to the max step problem referenced in Flannery's talk. So specifically, if in this case, excuse me, that G has order that's just even, 2 times an odd, if the matrix of the co-cycle has determinant meeting the Ehrlich Rorschach bound, then the co-cycle is quasi-orthogonal. Right. So, just to say a few things about existence of co-cyclic PCDs now. So these deep results by Isel were mentioned in Santiago's talk, proved using facility with character theory of finite groups. For Butts and Hadamard matrices, non-existence results for co-cyclic BH, there are some due to Ronin. But for quasi-orthogonal co-cycles, non-cobounded quasi-orthogonal co-cycles, we don't seem to have any such strong non-existence results. So perhaps this points to the existence problem, or perhaps quasi-orthogonal co-cycles being a bit more tractable than the existence problem for orthogonal co-cycles, of course, with ±1 coefficients. Okay, so that brings us to the last stage of the talk. So the most naive approach to the existence question for co-cyclic PCDs is to compute all relevant co-cycles and then go searching for those that give PCDs within that set. Of course, that's a hopelessly naive approach, and we don't get very far because of the exponential size search space and the fact that it's not enough to test. I mean, for example, it's not enough to test a single co-cycle from each cohomology class. But anyway, the algebraic problem of computing co-cycles is interesting in its own right, and I want to say a little bit about that before posing the final question, open problem. So just from the definition, we can write down all of the co-boundaries. Hope that's very straightforwardly. So what we're talking about here is computing a set of representative co-cycles for the second cohomology group. And there are several methods for doing this, and the good thing is that they're implemented in Magma and Gap. The approach that I'm most familiar with uses a standard result in 2 cohomology theory, this universal coefficient theorem. And I don't have time to get into all of the nitty-gritty of this, but just in summary to say that it decomposes the second cohomology group as a direct product of so-called inflation component, inflation part I, and a transgression part T. So if you want the explicit definition of I, there it is, and the transgression part. Now, just to define some of these things, so G dash is the commutator subgroup of G, and H sub 2 is the Schur multiplicator of G. And there are implemented methods for computing the multiplier. in particular for permutation groups G, that's not suitable for us. We work from a presentation of G. Yes, but here's the source of the final problem that I want to mention. The computation of the inflation part, this is completely canonical, up to equivalence, of course, as always, of the matrices, co-cyclic matrices. But computing the transgression component isn't. They're quite different looking matrices, non-equivalent for different choices along the way. The first of those choices is as a presentation for G. And then there's another one later on. So a presentation, just to recall, what we mean here is G is given as a quotient of free group F by a normal subgroup R, free group on the generators of G, and R is the normal closure in F of the relators in the presentation for G, words in the free generators of F. So this that's enough to pose the final problem. So we're seeking a characterization of co-cycles to deal with the fact that the computation of the full set of representatives is not completely canonical. So we're asking about a way to characterize co-cycles that are symmetric, almost symmetric. So here are the fairly obvious definitions of those kinds of co-cycles. And each of those types of co-cycles forms a subgroup, Z2. One obviously containing the other. And I haven't told you how to get I, but the representatives for the cohomology classes in I, these are all symmetric. So since every co-boundary is clearly almost symmetric, this means that the elements of I, each of those co-cycle classes, consists of almost symmetric co-cycles. And the question is whether the converse is true. Are all of the almost symmetric co-cycle classes in the inflation component, in the universal coefficient theorem decomposition we did, second cohomology group? And we don't have a full answer for that question. But in the situation that we've chosen a good presentation, that is one satisfying this property here, this diamond property, that this quotient, the commutator group of F intersect R modulo commutator of R and F, if this happens to be generated by single commutators, now certainly generated by words in commutators, but if it's generated by single commutators, then the answer is yes. That is, just to recall, that the inflation component, all of the almost symmetric co-cycle classes are in there. So I mean, to answer this question, we have to deal with the transgression part, and that's what I'm not going into detail about. But the source of this diamond property is another standard two cohomology fact theorem, this famous Hobbes formula for the Schur multiplier, which is that this thing here is exactly the Schur multiplier. Now, examples of G that have a presentation satisfying diamond, well, all abelian groups, thankfully, all metacyclic groups. But in general, right, otherwise, yes. So just one final remark, it's a side note, it doesn't help us with this final open problem, but this result by Lloyd-Becker, which implies that a cocycle class contains a symmetric cocycle if and only if it contains an almost symmetric cocycle. One direction is obvious, it's the other direction. Here it requires a proof, and it's yet another proof that there are several like it scattered throughout this area. Yet more nifty manipulations with the two cocycle defining equation. But yeah, as I say, that is just an interesting side note. And I've definitely filled up the allotted time, so that's it. Okay. Thanks.